So with the analysis of flow networks, my problem is that I have some sort of network, and what I'm going to be presenting here is going to be a network which could be for a water distribution network, a sewer system, drainage system, or an electrical network, those sort of networks which have potential-driven flows. Okay, these sort of networks are generally designed and have a known network structure, and if you're missing any plans, you can normally guess based upon the design standards where things should go. So one of the first things when analysing these networks is you need to choose which variables you are going to define as variables that you want to infer over or put your probability distribution over. Because if you chose every single variable within the network, the way that one draftsman draws it is different to another, and your inference would be different. And we want to get consistent and the same results irrespective of who analyses the network. So that's the first point. The second point with these networks we want to analyse them in a probabilistic way. So we want to be able to take into consideration that we don't know everything, and also we want to include data which we're potentially from measurements which we're uncertain about. So we don't want to just say this is the value, we want to say that this is what I think it is and this is my uncertainty, and then incorporate that into the analysis. So in my MaxEnt analysis, what I call a soft constraint is a constraint which is applied which impacts my analysis, but it is not strictly enforced. All right, so to analyse these networks, I'm going to be both analysing it using a Bayesian method and a maximum entropy method. I'm also mainly going to be looking at truncated distributions so that I'm not staying completely in the normal sense of just normal distributions with infinite limits. But I will also touch on some results from that particular case, and I'll present a case study showing the similarities and the differences between the two methods. All right, so we've got some good foundations for both the maximum entropy method and also the Bayesian methods. So our MaxEnt methodology is the standard methodology to find a probability measure over uncertainties of interest, construct a relative entropy function, identify constraints, maximize entropy, and extract moments that you desire. And we've got foundations and more foundations. And also we've got foundations for Bayesian stuff as well. All right, so now moving on to my actual analysis. So the first thing which I'm going to show is here. These are my flow rates. So I've assembled it into a vector, and this vector is all flow rates on the network. These are the external flows, and these are the internal flows. And external flows are those which are entering or exiting the network. Okay, the next point which I'm going to highlight is that X is the subset of flows which I'm going to choose to define over my probability distribution over, and X bar is the flows which are in the network but I'm not defining my distribution over. And if I've still got the interactions which are going on the network which aren't within the probability distribution, but I still need to incorporate their effects within the probability distribution. And this bit of maths here allows me to work out from my probability distribution what the flows are within the network from those which I'm inferring. And I've got so these matrices which you'll see working throughout, I've got conservation of mass, I've got loop laws, I've got observed flows, and I've got observed potential differences. Okay, so to begin my analysis, I am going to choose 3 different cases of priors which I'm going to apply, and I'm going to apply the same prior to the Bayesian model and to the maximum entropy model. So I have a truncated normal distribution, a truncated exponential distribution, and a beta or Dietrich distribution. And I'm going to be referring to these prior distributions as the cases which I'm talking about throughout the rest of the presentation. Okay, so to incorporate my conservation of mass and loop laws within my system, within the Bayesian analysis, I'm going to use delta functions to incorporate this information because I'm very certain that conservation of mass and effectively conservation of energy are going to hold. Okay, now for incorporating any potential differences or observed flow rates, I'm going to be using some fairly interesting likelihood functions. So for the truncated exponential case, truncated normal case I'll begin with, it's going to be fairly straightforward. It looks exactly the same as though it had infinite limits due to the parameters I'm choosing, but this here is a scale parameter, and this observation is a mode and not a mean, or a location parameter because it's truncated. For the truncated exponential case, I have this interesting function, and for the beta prior case, I have another interesting likelihood function. And it's a similar sort of function, exchanging variables if I am working with potential differences rather than observed flows. And these functions allow me to incorporate some sort of mean or mode sort of flow rate observation with some uncertainty about it. Okay, so going through the maths to calculate my posterior using the truncated normal case, I work through it exactly the same as though I would by completing the square as though it was with infinite limits. But my results given down here, that's a location parameter and that's a scale parameter. I then need to use some numerical technique in order to be able to get out my means and covariances, which I will show when I get to the case study. Truncated exponential and beta posteriors. Well, this one fails at this stage because if you look here, all of my second order terms come out from the conservation laws, which are delta functions, which then results in this section here being rank deficient, and I can't invert it, which means my analysis has finished there. I will just add, though, in the MaxEnt case, this particular prior can actually continue through. It's just stuck here due to trying to use delta functions to enforce conservation laws when I don't have another matrix in the system which is positive definite, which would allow me then to invert it like I do in the truncated normal case. And my posterior for the beta case, I'm not even going to try to go any further than that without going to numerical methods. All right, so now I'm going to go to the maximum entropy derivation. So I have my variables of the network which I've chosen, which is subset of the flows on the network. But to incorporate my soft constraints, or constraints which do not need to be held exactly, I have additional variables which I've defined for the PDF for observed flows and observed potential differences. I then define an entropy function over those flow rates, and my constraints are normalization, Kirchhoff's first law, Kirchhoff's second law, and then if I'm going to incorporate any flow rate observations and any potential difference observations. And this section here is which links on the network am I working with. That's my flow rates on the network, and here I've got my observations, which is all this here is going to be some mean value of my inferred distribution when I solve that. Anyway, forming my Lagrangian and optimizing it, I get this inferred distribution where I'll have my prior multiplied by what comes out of the maximum entropy method. Okay, so this is the analysis where I'm using the truncated normal. So I pretty much just go through and follow the process. So I've just multiplied in my prior and form I get where I have my vector of Lagrange multipliers, which I need to solve for. And I'll need to use numerical methods to solve for them, excluding the case where I have infinite limits, which is what I'll move on to. So with infinite limits, I can continue on, and I end up getting a mean posterior of this with this Lagrange multiplier, which can then be put up into there to get the entire thing. So let's do, first of all, with infinite limits, a comparison between the means obtained using the Bayesian method and the maximum entropy method. And nicely enough, they actually come out to have equal means in the case of infinite limits. And that can include as many covariants as you want within your observations. Okay, so now I'm going to move on to my case study using non-infinite limits with the priors which I mentioned earlier. So here's my network. With this network, I chose the flows which are entering the network, or exiting, as the variables which I was going to find my probability distribution over, or x. The internal flows can be found from my probability distribution. All right, I set up mean of my prior in all cases to be 0, and with the normal distribution, I use the location, or I've used the location parameters directly as what I'm going to work with, whereas I use means and variances with the beta case. So with the truncated normal distribution, I've truncated between -1 and 1, and I've applied the Bayesian approach, and I've also applied the MaxEnt approach. And here I've plotted up the MaxEnt results in blue and the Bayesian results in red. And in the center, where they're a long way away from the limits, they are pretty much identical. As we approach near the limits, there's a slight difference between what I get from my soft constraints in MaxEnt and my what I get from my Bayesian analysis. Using the beta case, I get fairly similar sort of behavior, so quite close in the center, but again, I've got a difference up near the limits as well. Now looking at the marginal distributions. So Here I've got the marginal distribution, so for each of the flows. So that's the inflow, which is the flow which I constrained. And these here are related to, through the delta function, come out. And this is for a constraint flow rate of 0.9. And over here I have the same thing with the MaxEnt. So the MaxEnt methodology has an extra dimension. So in my marginals, I've got my internal flows within the network, and I've also got my observation, which has been constrained to have the same mean as the variable within my network. Now, the way that the interactions between variables within the two methods is quite different. Within the Bayesian case, the interactions between variables are incorporated through cross terms. So that means that if I look at the full PDF of this, it's going to have some very sharp peaks because I've got delta functions in there, and it's going to have covariances and I have to treat it jointly. I have to integrate this thing as a whole in order to be able to get the moments out of my posterior. Whereas in the MaxEnt case, the interaction between variables are incorporated within the Lagrange multipliers, and that means that I actually don't have any cross terms within my probability distribution. And as I have no cross terms within my probability distribution, I can actually integrate each variable separately. And so what that means is, using this methodology with the proposed constraints which I've put out, you could do a 1,000-dimensional integral on MaxEnt by 1,000 one-dimensional integrals, whereas if you had to do a 1,000-dimensional system using the Bayes method, you would need to treat the 1,000-dimensional integral jointly, which would then result in fairly substantial computational saving, assuming that you're happy with your prediction, in the sense that obviously if you're going to be taking draws from your distribution, you're going to have you're going to be drawing, not in fairly straight sections. You're going to have quite a spread over the cross dimensions. All right, well, thank you.